Good morning, AP Chemistry fans. This is another day of AP Chemistry lessons brought to you by Sean Byrne from Glenbard West High School outside of Chicago. I am wearing my hat and gloves today because even though it is Wednesday, April 15th, this is what my backyard looks like. We got almost an inch of snow. We have these beautiful flowers that had been blooming over Easter time, and we're still going to have to break out the shovels again to try to get all this snow off. So I hope that wherever you are, whether it's in the Midwest or out west, I hear there's a lot of snow too, or East Coast, you're getting ready for it. I hope that you're safe and able to enjoy a little bit of this fun weather for the next 35, 45 minutes today. We're going to take a look at some really fun chemistry from Unit 5 in kinetics, continue our conversation of Unit 5, and then give you some homework problems and look forward to another day of chemistry tomorrow. So just as a quick review of our website where you should be looking to get all your information about our upcoming AP exams. You see all the 8 different things that are over here on the right-hand side. Make sure that you're checking in for students that don't have a device or don't have internet access. Look at your scoring and earning credit and things like that. All of that is available to you at apstudents.org/exams 2020. Of course, we're all looking forward to Thursday, May 14th, when we're going to all be taking a 45-minute exam on our own devices. It'll be completely free response, and all of the specifics are here on this slide. This is, I imagine, for many of you, a repeat of things that you've seen multiple times before, but go ahead and check it out or go to AP Central for any further questions that you have. Our lesson overview for today is going to be the same as the same pattern that we've talked about that we've used for our whole time together. We'll do our warm-up where we review the material from yesterday, the homework from yesterday, some AP problems. Then we'll go through some new content and give you some opportunities to practice. And then I'll give you some AP exam practice to look at tonight for homework or this afternoon in preparation for class tomorrow. Of course, if there's any time that I'm going too fast and you want to stop and rewind, I encourage you to. There's going to be several opportunities today where I'm going to ask you to stop and answer a question on your own. So feel free to hit that stop button. I hope you have a pencil and paper next to you so that you'd be able to take a look at, to be able to work out some of the problems that we're asking you to do today. Okay, so let's get to our warm up. No, sorry, let's just review. We're going to continue on with Unit 5, looking at kinetics and specifically kind of all generally around reaction mechanisms and how that relates to the material that we talked about yesterday with rate laws. Okay, so our warm-up, there were 2 different things we asked you to do. One was to consider some data in order to determine the rate law and the rate constant. We maybe wanted to make sure that we said it including units from the equation below. And so if you haven't had a chance to look at this yet, pause, see if you can determine the rate law, can calculate the constant and then calculate the units on the constant. I'm going to go through my solution with you right here in just a sec. So what we want to make sure we do when we're looking at our data is to isolate different trials in such a way that one of the variables is changing, one of the reactants is changing, and the other one is not. So I'm going to isolate trials number 2 and 3 here because I notice that the NO, nitrogen monoxide, is not changing. So this is the concentration of nitrogen monoxide is not changing in between those 2 different trials. Okay, remember each line of this data table represents a different set of data that were collected from a different experiment, right? So this experiment had 3 different trials, or at least 3 different setups. And so in between these 2 trials, there was no change in the nitrogen monoxide concentration. But what we notice here is that the hydrogen was doubled in our experimental setup. So that was how the experimenter set up. That would be like their independent variable. And then the data that they collected, or their dependent variable, is the rate over here on the right. And what we notice is that the rate doubled when the concentration of hydrogen doubled as well. And so what we can conclude from that is because they both doubled, because they both changed by the same variable, that the order with respect to hydrogen is a 1. Okay, remember that there's the trick here is to make sure that just because you see a 2 there, just because you see them double, doesn't mean that the order is a 2 as well, because what we're looking for is the relationship between how the reactant changed and how the rate changed. And if they are the same, then what we can say is that that is a 1. Okay. If then we'll look at experiments or trials number 1 and 2, and we would do that because we see here that hydrogen did not change, but the nitrogen monoxide doubled. Okay, so double check and look at your work there. You may want to look at the rates and see if you can, just off the top of your head, if you can conclude how the two rates compare to one another there. It turns out that this is a factor of 4, which could also be considered 2 squared. What we see is that when the nitrogen monoxide doubles, the rate quadruples, or it goes up by a factor of 2 squared. We went through a practice yesterday where we calculated out, when the numbers are not real easy, how you could set up a problem. So if it doesn't jump out to you that the order for nitrogen monoxide in this equation is going to be a 2, you may want to go back to yesterday's lesson and see how we set up the problem in such a way that we were able to solve for that exponent a little bit. It's a little bit more of a complicated process. In this case, you may just want to say, oh, this goes up by a factor of 2, 4 is 2 squared, and so that tells us that this that the exponent on here, or the order with respect to nitrogen monoxide, is a 2. Okay. Our next step would be to calculate the rate constant. I'm going to do the number and the units separately from one another. Okay. Here's my math for how I would solve it. We're just going to take any of the 3 trials and we would plug in our numbers. Okay. So I took the rate, plugged it in here. I left k because that's what I'm solving for. I plugged in my 0.7 with my exponent of a 1. This is where a couple of mistakes could easily be made if you forgot to include your exponent of 2 here. 0.6 squared. We're going to solve for k. And then when we do this math out, we're going to divide 2.2 times, or 2.286 times 10 to the minus 2 divided by the product over here. Make sure either you put parentheses around both of these, or you divide twice in your calculator, just to make sure you get to a 0.09 as the value for k. Okay, and you should be able to go through trials 2 and 3 and get the same number, right? Because if it's a constant, it's a constant. And then let's look at how we would calculate our units. Okay, so we have we've determined that this is what our rate law is going to be, or these are our exponents. I'm just going to plug in only my units and then solve for k. So if I go back to my data table, I'm going to see that the rate is molarity per second, or moles per liter per second. Okay, and that my concentrations were in moles per liter. I'm going to distribute my exponents here as well, so that I can say, I'm sorry, I guess I distributed my exponent, and I'm going to divide both sides here. So I brought this over to the other side. Moles per liter stays the same, but I have moles squared times liters to the negative second, right? I just distributed this 2 across everything. And then I'm going to cross out where it's applicable. So moles would cancel out with moles. Liters to the minus 1 cancel out with liters to the minus 1, and I'm left with seconds to the minus 1 over moles squared times liters to the negative second. So I'm going to simplify that to be liters squared over moles squared times seconds. And typically we write this in an AP test with negative exponents rather than as fractions. And so you would get something like liters squared times moles to the minus 2 times seconds to the minus 1. Okay, now this is a very complicated set of units for a rate law, and that's because it's a 3rd order rate. If you go back to our review of our lesson from yesterday, you notice that I just talked to you about the units for a 0, a 1st, and a 2nd order reaction. If you were going to memorize anything, those might be things you'd want to memorize. I think what I mentioned yesterday is that I'm not a big fan of just memorizing things for memorization's sake. So the reason why I gave you this one, even though it's maybe a little more complicated than you would be asked to do on a typical AP test, is so that you know this process. So that if something were thrown at you, a 3rd, a 4th, however complicated the equation is, you should be able to follow this process in order to get to your units. Another trick that I've seen happen in a couple other AP tests, excuse me, go back to this, the units of time can change, right? So sometimes you measured, I think we saw one yesterday that was in units of hours. It was measured in hours instead of in seconds, could be measured in minutes, could be years, right? So you just want to be really aware of how this time variable might change. Typically, we don't look at any other concentration rates other than moles per liter, but this time variable can change. And that's why having a process like this, where you know what you're setting up, is an important skill for you to have. So our final answer here would be that the rate is equal to 0.09 liters squared moles to the minus second times seconds to the minus first. H2 to the first power. You could probably leave that one off because we know that that's implied if there's no exponent, that it's just to the first, and then NO to the second. Okay. Our second problem was right off of an AP test. We had several different questions that we were asking you to do. I believe that there's 3, if I remember correctly. And the first one is just to look at these graphs and to be able to determine what the order of the reaction is with respect to the blue food coloring. So we have some blue food coloring that's reacting with bleach to produce something that is colorless. What I really liked about this is that we brought in some of our spectrophotometry, okay? And so what we remember, again, go back and check out your earlier lesson about spectrophotometry, is that absorbance and concentration are considered are proportional to one another. So we have, this is measured in absorbance, the natural log of absorbance and the inverse of absorbance, but we can use those as stand-ins for concentration, natural log of concentration and inverse of concentration, because that's how spectrophotometry works. Okay, well, I'll go back to that in a minute. So based on the above, what is the order of the reaction with respect to the blue food coloring? We're going to highlight this one in the middle here because we see a straight line, and the straight line, as we learned yesterday, would be, well, we're going to look between these 3 graphs, find the one that is the straight line, and then we should know that if it's natural log versus time, that's an indication that it is a first order reaction, and certainly first order with respect to the blue food coloring. You see how that says with respect to the blue food coloring down there. Okay, go back and check out some of our review from yesterday if that part wasn't making sense to you. The second thing is that we're told that it's first order with respect to bleach. Of the 3 things that are possible down here, increasing temperature, increasing food coloring, and increasing bleach, which one would, in essence, slow down the reaction? When the solutions are combined, the solution observes that the reaction mixture reaches an absorbance near 0 too rapidly. And so what we're trying to do is we're trying to slow this reaction down in order to be able to collect better data. Looking at our factors that affect the rate of a reaction, we would expect that increasing the temperature is going to increase the number of collisions, right? And would in effect make the reaction happen faster. Okay, increasing the bleach, in this example, we already have bleach is at such a large excess that it's essentially constant throughout the reaction. And so it turns out that increasing the food coloring is the best way to increase the rate of the reaction so that it doesn't, to decrease the rate of the reaction so it's not happening so fast, because it's going to give us more time, or this reaction more time, for the bleach to oxidize the food coloring that is there. It was an essentially running out of blue food coloring too quickly for the absorbance to catch up, or for the spectrophotometer to be able to measure what's happening with this reaction. Okay. And then the last question gets at a third, I've given away a little bit of the answer there. The student wishes to study the oxidation of red food coloring with bleach instead of blue food coloring to bleach. And how would we need to modify this original experiment in order to determine this reaction? So I'm not sure where the floating head on the screen is, but if you wanted to go back and notice underneath this red box, or just to the side of this red box, you should see that the student used a spectrophotometer set at a wavelength of 635. Now, you would not be expected to connect that to a particular color, but I'm going to show you the same spectrum that we showed you earlier on this year, just so that in your brain you can kind of get the connections there. So 635 nanometers of light corresponds to roughly either a very dark red or moving on to yellow. It would be right in this range over here, right? And that makes sense that typically in spectrophotometry, when you have a color of the solution, you would pick a wavelength to measure that is on the other end of the spectrum, or pretty far away from the color of the solution that you have. So in this case, we had a blue color of our solution. The experiment, as it was done, used a wavelength of light that was pretty far away from it. If you change the color to a red food coloring with bleach, all we would want to do is change the wavelength at which we measured the concentration or the absorbance of the solution, and then we're able to surmise the concentration from there. And so the answer would be, you would set the spectrophotometer to a different wavelength. You would not be expected to say anything more specific than that. You would just, if you wanted to add into a wavelength that is further away from red, or that was on the opposite end of the spectrum or something like that, that would be fine. But in terms of saying, you would not be expected to say, oh, 635 nanometers is red. We're going to move it from red back over to blue to 450 or anything like that. That's beyond the specifics that are needed. We want you to recognize that spectrophotometer works best when the color is different from the color of the solution. Because we have a red food coloring here, we're going to have to pick a different wavelength of light. All right. So that was our review of our four problems from homework last night. Here's what you need to know, and give you some guided practice on our 4 topics that are here. Like I said earlier, this is all has to do with reaction mechanisms. Our skills that we're gonna determine some balanced chemical equations, look at a different way of viewing chemical equations, describe the components of models. So I'm going to show you a number of different models. We're going to apply the theory to that in 2 different ways. This is going to become a little bit mathematical, but nothing where we even need a calculator today. It's just kind of equations and rearranging some equations today. Okay. So getting to it, what we want to understand is the difference between an elementary reaction and an overall reaction. And so what we can do is kind of consider, why is it in the data that we have looked at over the past yesterday and today, why would it be that a rate law may or may not include all of the reactants in a reaction that we've been given? So if something was 0 order, or was 0 order with respect to one of the reactants, or it was 2nd order, even though the reactant only appears once doesn't have a coefficient in front of it, why do things like that happen? And when we look at the mechanics, when we use that word mechanics or mechanisms of a reaction, what we're doing is we're looking at the steps that physically happen within a beaker or within a reaction vessel that talk about how a reaction actually happens. And so you typically will see something like this. Like, here's an overall reaction. Hydrogen gas reacts with monoiodine monochloride, or iodine monochloride, to make hydrochloric acid and iodine. Okay. And a group of scientists may study this reaction and realize that when this reacts in a vessel, what actually happens is one hydrogen molecule reacts with one of the ICLs to make some HI and some HCl. And then a second step that happens is that one of these HIs reacts with the other ICl in order to make some hydrochloric acid and some iodine. And so what we have here is actually 2 different steps, and we would call each of these an elementary reaction. So these are not the overall reaction. We're going to talk a little bit later about how we may add these up in order to come up with an overall reaction. If we were to do that, we would see that there's of these 2 steps on the 2 steps below, there's a hydrogen gas that corresponds here. There's 2 ICLs that correspond to the ICL here. There's 2 hydrochloric acids and an iodide, and that this thing HI, hydrogen iodide, sort of strangely appears out of nowhere. And we'll talk about how we can characterize that as an intermediate in a minute. Okay. But what we can do is we can look at each of these intermediate steps or these elementary steps and say, what is the rate for, what would be the predicted rate for each of those elementary steps? Okay, so we wouldn't do this for the overall reaction, but we could say for step number 1, what could the rate look like? And it turns out that the rate for step number 1 would look like the would match the coefficients on the balanced equation. Okay, so for this step alone, the rate would look like 1 hydrogen, or hydrogen to the first, 1 ICL, ICL to the first. And similarly, we could do that, the same thing for the second step. And then we'd have to do further experimentation in order to figure out which one is the best predictor of what happens with the overall. And that's a question we'll answer before the end of today. Okay, so a key thing that we're doing here is we're looking at an elementary reaction, which is one of the steps in a proposed mechanism, and we're able to write the rate law based on that, not necessarily on the overall reaction. And we'll use that to help us inform us later about what's happening with the overall reaction. Okay, so let's just practice this real quick. The same idea. If each of the 4 on the left-hand side are elementary reactions, can you predict what the rate law would be? Give you a second to stop or to write them down real quick before I go through my answers. Okay, so for this first one, we would expect, based on that, where we have a b to the second, the rate is equal to k times concentration of a times concentration of b to the second. So this 2 becomes an exponent up here. We could do a similar thing for just a general reaction where it comes to a third power. Reactions with a third order reaction rate is very, very rare. So you typically don't see a lot of those. You'll see a lot of 1s and 2s. Okay, we could have there's similar to the one I just showed you on that last page. There's 1s are the coefficients on each of these, so these correspond with an exponent of 1 here, and then our rate similar for nitrogen monoxide with a 2 and hydrogen gas is a 1. Okay, so remember that our rate laws only correspond with the reactants, so we don't really concern ourselves with the products here, and we can look at the stoichiometry to help us predict what's happening in the rate law. Okay, now I'm going to jump ahead to talk about how we're going to decide which one of these we should use, right? And I said earlier that if we're looking at this reaction, we would need further experimentation in order to figure this out. And the important piece of information is we want to know which of these happens quickly and which one happens more slowly. And what we will consider is that the slower reaction is what we call the rate determining reaction. So the key piece of information for this reaction, this mechanism that we already looked at before, is that step number 1 happens at a slow rate. And so you would either need to be told that, given a set of data that looks at step number 1, it takes much longer amount of time. And so that's kind of the holdup for this whole overall reaction. And so our overall reaction rate for this mechanism, it would correspond to whatever the slow step is, or would correspond to what we call the rate determining step. Okay, so if you were given a reaction that looks like this, or a mechanism that looks like this, you might be asked to consider what's here and identify which of them represents the overall rate that is consistent, the rate law for the overall reaction that's consistent with this proposed mechanism. And what you'd want to do is you want to identify that this is the rate determining step. It's the slower step, right? And so the rate would be equal to K, some constant, times HBr times O, the concentration of HBr times the concentration of O. Okay, so we're always just going to look for at least for right now, I'll show you one exception to that rule in a couple of minutes, but in general, we're going to look for the slow step. We're going to define that as the rate determining step and write our rate from there. Okay, here's one more example of this. We're given the overall reaction up above. We have a proposed mechanism that has 2 steps. Go ahead and write your rate law based on what's here. And again, we would identify that that's the slow step or the rate determining step and write our rate as NO2 times F2. Okay. I know that this seems pretty straightforward for right now. We're going to look at, again, like I said, a little bit of a trickier problem in a couple of minutes, but it is pretty straightforward that we want to look for the rate determining step, which would be identified as the slower step, and we relate that back up to our overall rate law mechanism. And here's where you see some discrepancy between this rate law, where it's a first order for nitrogen dioxide, even though there's a 2 on here. So it matches the coefficients on the elementary step, but does not match the coefficient on the overall reaction, which is why we need to have, we didn't talk about this yesterday, and it's why we need to have these steps here to connect the elementary step to the rate law, not the overall reaction. Okay, and so if we had a bunch of experimental data on this, that would correspond to this rate law. So let's look at some particle pictures as a way to kind of define what's happening in each of these steps. Okay, and there's basically 4 different, maybe we might want to call them vocabulary words, 4 different ideas to connect each of the reactions that's in front of you. Okay, so if we rewrite a reaction that maybe you're used to seeing of ozone that's breaking down in the upper atmosphere, this is one mechanism, one way that could happen. We're pretty comfortable identifying that even in both of these steps, we have reactants. Okay, so that's ozone, that's O3, 3 oxygens that are together. They are the substances that appear only on the left-hand side of both of the steps, right? And then similarly, we could probably look at all of this O2 that is over here, and we would be able to see those as the products of this overall reaction. Okay, and so if we were writing an equation for this, we may write two O3s turned into 3 O2s and be done with it. But that wouldn't tell you the whole idea behind the mechanism, behind what's actually happening with the particles in the atmosphere. And it turns out that there's 2 other important pieces that are happening in this reaction that these mechanisms help us to identify. The first one is the fact that we have this intermediate. Okay, and so this intermediate is something that appears as a product on one of the earlier steps, and then is a reactant on a later step. We only have 2 steps here, so it's the one immediately after it. If you had a 3-step mechanism, or maybe even a 4-step mechanism, it'd be really complicated. They don't necessarily need to be next to each other, but what we're going to see is that it appears as a product first, and then is used up again. So if I let this reaction go to completion, if this is something that goes to completion, if all of the reactants are used up and made all products, I wouldn't necessarily have any, this is what, NO, 1 nitrogen and 1 oxygen. I wouldn't have any of them in my overall reaction, and I might not measure a significant quantity of it even in the middle, sorry, at the end of the reaction within the container. But if somehow I was able to look inside a container of gas, I might see for split seconds here or there some nitrogen monoxide, some NO that's there. And that's because it's an intermediate. It gets created and then used up almost as soon as it is created. Okay, so if this is, again, here we look at a slow step, this takes a little while to do, and then this is fast. So as soon as any of these are created, this is used up again. So it's what we call an intermediate. We see this other substance, the nitrogen actually here, that we can call a catalyst. It interacts or reacts with the reactant. This would be considered what I think tomorrow we'll call a homogeneous catalyst. So it's in the same state as everything else that's there, but it remains unchanged. And so it's a reactant at the beginning in a first step, but then it gets produced again as a product later on in the mechanism. And so it essentially is not changed. So we have some nitrogen atoms here that help along this reaction, but we have not changed the amount of nitrogen that is in the atmosphere, or the amount of, not changed the from beginning to end, how much nitrogen is around. So if we're looking at a catalyst appears as a reactant first and then as a product, whereas an intermediate appears as a product first and then a reactant. So let me give you another example of this and see if you can identify which of the substances here are reactants, which are products. Identify if there are any intermediates, and if there are any catalysts. Pause for a second and see if you can draw your own arrows in here. Okay, and I'm going to go through. We have some reactants. Here's a good example of some reactants that are actually appearing in the second and the third step. Okay, so those are hydrogen atoms that are here. So we have some oxygen and nitrogen up here, and this is some hydrogen that's reacting. Those are our reactants. Okay, our products can appear in several different locations. So we have lots of water that's getting produced. Okay, and let's see if you identified, we have two actual intermediates in this reaction. One of the intermediates is there. We notice that it appears as a product first in step number 1, and then as a reactant in step number 2. And then a second intermediate that is a product in step number 3 and a reactant in a product in step number 2 and a reactant in step number 3. Okay, so whether you're able to identify what these compounds actually are or not, just seeing that they are intermediates, both this and this are intermediates, it turns out that this is N2O2 and this is N2O. But identifying both of them as intermediates is important, okay? And unfortunately, in this example, there isn't a catalyst that's there, right? We don't have something that would appear as a reactant first and then gets produced again or is left over. Let's move on to an example where we're looking at chemical formulas rather than at particle pictures. Identify reactants, intermediates, products, and catalysts. Go ahead and stop your video just for a second to do that. Let's see, our reactants are here. Products are here. We have an intermediate here. And we don't have a catalyst there. So these are these four questions you would want to ask yourself every time you look at a mechanism, which are reactants, intermediates, products, catalysts. Okay, and then I have one last example here. Give you a hint that this one actually does have a catalyst. Go ahead and identify your 4. Pause if you need to. Here are the reactants. Notice that this is sort of a strange one oxygen by itself. That doesn't happen very often. I wanted to leave that to last because I knew it might mess you up. You might think that I left a 2 off of there, but it actually is just a monoatomic oxygen floating around out there. Products are here. So we've got O3s turning into O2s. Okay, here's an intermediate because it appears as a product first and then a reactant. And then finally, I found you one that has a catalyst. It starts as a reactant up here, but we produced it over here again, and it is unchanged. And so that is not, would not appear necessarily even in the overall reaction. All right. So there we go. Now, I do want to take a brief minute to look at what we call steady state approximation. What we're looking at here is a mechanism that looks a little bit different from our other reactants. So I want you to just take a minute to look at this mechanism here. We've got 3 steps, and consider, based on what we've done so far, what would you expect the rate law for this reaction to be? And I would suspect that many of you would notice that this second step is a slow step. And so you would write a rate that is going to say the rate is equal to K times the concentration of NO2F2. Okay, now there's a little bit of a problem with that. And I'm going to want to tell you the 2 reasons why we would not consider that the rate, and how this mechanism is different than the other ones we've looked at. Okay. First of all, I'm going to notice that this is actually, now that we have that vocabulary word, now I'm going to notice that this is an intermediate. Okay, and intermediates, like I said, will appear for a split second. Okay, and they typically are not used in a rate law. Okay. This can't be the rate law because it includes an intermediate, so we would not put it in there. The other thing that's different here is that we're starting with an equilibrium up here, right? So we have 3 steps here, but this first step is an equilibrium, kind of a reaction rather than one that we would expect to go to completion. And so when we combine those two things, we're going to have a little bit different of a mathematical process in order to determine what the rate law is. And what we're basically going to do is determine how can we relate this intermediate back up here to the step above it in order to write our rate law. And the math is going to get a little bit wonky here, so try to stick with me. This would be a great example. I'm going to give you two examples, but you might want to listen to this just a couple of times so that you can, before you practice our homework for tonight. Okay, so here's our three steps. Okay, I just had to scrunch the screen so we could fit a couple of steps in here together. Here's what that rate law is, what we might have considered the rate law was based on this slow second step, right? If I were to look at the first step, what I know is that the forward rate is equal to the reverse rate. And that's just our definition of equilibrium. We're going to get to a pretty big discussion of equilibrium over the next couple of weeks. I imagine that most of you did talk about equilibrium in your classes already. But one of the fundamental understandings of a reaction that's at equilibrium is that the forward rate and the reverse rate are equal to one another. So if we were to write our forward rate and our reverse rate in our normal rate law form, we would see that our rate for the forward step or forward reaction would be K forward times the concentration of the reactants here. And that is equal to the K for a reverse, these Ks, not necessarily the same, using this NO2 F2 concentration is connected to the reverse. And what's nice about this is all I've done is I've said our rates are equal to one another because it's equilibrium. I've used the same rate law that we've talked about for 2 days now, okay, where I looked at a K, identified a K for the forward reaction. I looked at our concentrations for the reactants for that reaction. And I'm going to rearrange it in such a way that I'm just solving for NO2F2, right? So the concentration of NO2F2 is equal to, follow my math here, K forward divided by K reverse. So what did I do? I divided both sides by K reverse. So that quantity times the concentration of N2, or concentration of N2 times the concentration of F2. Okay. And so now I can take, if the concentration of NO2F2 is equal to all of this stuff over here, I can just substitute it back in to my equation on the left-hand side. And then I'm just going to probably simplify it and say that there's a new K. Say I identify this as K2. This K that's here, excuse me, is equal to the product of K2 times these two Ks that are over here. Okay. And so this would be the rate law for this kind of a reaction. Again, it's the two stipulations here that we're looking at an intermediate in the slow step, and we're looking at equilibrium in the first step. Okay, so stop now, read through my explanation of the math here again, if you would like, or here's another similar example that I would encourage you to look at. See if you can solve the math here on your own. It does take a couple of minutes to go through, so go ahead and pause so that you're able to go through the math. And my solution to this would be similar to what we did before. The trick here is that we would write our rate as NO-BR2. We're going to include NO times BR on this side, BR2 on this side. Okay, so our forward and reverse rates are equal to one another because it's equilibrium. We're going to substitute this back in, and we would end up with a rate law that looks just like that. Okay, and we have a similar kind of redefinition of what's happening with our K. Okay, so take a look at that. Take a look at these two examples that we just gave you. We ran through a number of different things about mechanisms in here, and we should be able to see I had a couple of different problems or a couple different practice problems as well. Here are some AP practice problems for tomorrow. What I'd like you to do, this is a little bit different than the way that we did it before, but you'd have to identify both your intermediates and your catalyst, if there is one, in order to identify kind of backwards. We're going to work backwards to find what is step one. And then your AP exam practice is looking at a reaction of nitrogen dioxide according to that reaction. But what we have is a mechanism. And this, what's nice about this is that this will combine the things we've done over the past 2 days. Explain how the graphs indicate that the reaction, I'll read that to you. The reaction is second order here. So we're told to us that the reaction is second order, then write the rate law for the decomposition of NO2. And now we have 2 different mechanisms in what we're asked to do. Notice that this mechanism has 2 arrows in it. This mechanism is a fast equilibrium. So we'll want to look at that. And you'd have 2 different justifications that you'd want to answer. And what we'll do is we'll look at that in class tomorrow, okay? So remember that if you have any questions, you want to go back to apcentral.collegeboard.org. We've got a bunch of extra links that are down there. And you have, if you have students or friends that are having problems with the internet or problems with their device, go ahead and look at cb.org/tech, and we will get them the help that they need. Thanks so much for watching. I know this is a little bit shorter than our lessons have been in the past, so you get a little bit of a break to get started on your homework for today. Have a great day, stay safe, and I hope you're staying warm out there. I got to find my gloves and hat and put them back on before I go outside. Have a good day. I'll see you tomorrow.